We're going to go on to chapter 5 now, but before we do, they've added, the College Board added a topic to the AB curriculum a few years back called L'Hopital's Rule. L'Hopital's Rule in our book is covered in section 9.2, but we have enough information to cover it now that we know how to find all the derivatives that we need. So we're going to talk about it right now. So this first part's just kind of is a description of exactly what you need to know about L'Hopital's rule and its uses. So first of all, L'Hopital's rule is a way of finding limits. Now, we worked on limits and continuity in chapter 2, and there were problems that were difficult for us to do because we didn't know this rule. We could still do them using our calculators or intuitively, but this offers us a better way of doing it. I think you'll really like this. So it's used for finding limits when you substitute and you get an indeterminate form, 0 over 0, which we don't know what that's equal to. It also works if you have either positive and negative infinity over another positive or negative infinity. Okay? Now, excuse me. Suppose f of a and g of a are 0. Okay, so in other words, if I've got the limit of f of x over g of x as x approaches a, suppose you substitute both of them in and you get 0. Okay? As long as f and g are both differentiable on an interval that contains this letter a, and that g prime of a does not equal 0, then we can do this if the latter exists. So instead of trying to figure out what this is, we can say, okay, well, if I get 0 over 0 when I substitute, then I'm going to redo this limit using the derivative of f and the derivative of g. Okay? So you see why we couldn't have done this in chapter 2, because we didn't know how to find derivatives at that point. So when you apply L'Hopital's rule, look for a change from 0 over 0 into something else. If you do L'Hopital's rule and it's still 0, 0, then you can do it again. Now, most of the examples I'm going to do are going to be 0 over 0, but you'll also see in your book there are some times when you substitute and you get the top approaches positive or negative infinity and the bottom does also, and you can use this same approach. So let's check it out. Now here's a problem that we did, were able to do early in this year. We try to substitute negative 2 in and we get 0. And then we try to sub negative 2 into the bottom, you get 4 minus 4. That's also 0. Now the way we did it back then is we said, okay, well, then what I'm going to do is I'm going to try to eliminate the factor that's causing these to be 0. So I get x plus 2 over x squared minus 4, which factors as x plus 2x minus 2. And now we can see that if I cancel out these x plus 2's, I now have the limit as x approaches negative 2 of 1 over x minus 2. Now I can substitute and I get negative 1/4 for an answer. Now you can still do that for a problem like this. However, here's another option. Because I've got 0 over 0, and that's the key, you can't use this any old time you want to. It has to be an indeterminate form, like 0 over 0 or infinity over infinity. So if I were to say, all right, I get 0 over 0, so what I'm going to do is use L'Hopital's rule. I'm going to take the limit as x approaches negative 2 of the derivative of the numerator. Don't use a quotient rule. You're not finding the derivative of the whole thing. You're finding the derivative of the numerator and denominator separately. So the derivative of x plus 2 is 1. The derivative of x squared minus 4 is 2x. Now if I substitute negative 1, I get 1 over negative 4, which again is negative 1/4, offers us a different way. Now, why do we need two different ways to do the same thing? Well, because sometimes this first method doesn't work. Look at the second example. I put in 0. 0 cubed is 0. I put 0 in the bottom. Sine of 0 is 0. Minus, substituting 0 for x, I get 0 over 0. Well, how are you going to get anything to cancel in this one? It's not possible. So here, L'Hopital's rule is kind of crucial. So we take the limit as x approaches 0. Notice I write down this limit every time. Some of you get lazy and you decide, well, I don't have to write down the limit. Yes, you do. You wouldn't say, you know, Well, I have 4 and 4 equals 2. If you're taking the square root, you'd write the square root of 4 equals 2. Write things down. Don't expect people to know what you're doing. So the derivative of x cubed is 3x squared. The derivative of sine x is cosine x minus the derivative of x, which is 1. So now watch what happens though. I try to substitute again. 3 times 0 squared is still 0. Put 0 in here. Cosine of 0, that's 1. 1 minus 1, this is still 0 over 0. Never fear. If I get 0 over 0, I can use L'Hopital's rule. Do it again. So now I've got the limit as x approaches 0 of derivative of 3x squared, which is 6x, all over derivative of cosine is negative sine x, and derivative of negative 1 is 0. Again, I'm sorry about this cough. Again, I get 0 over 0. What the heck? Well, let's try one more time. So I take the limit as x approaches 0 again. As long as I keep getting 0 over 0, you can keep doing it. Derivative of 6x, well, that's 6. Derivative of negative sine x is negative cosine x. So finally, I'm not going to get 0 over 0. You can tell because the numerator is 6. And the cosine of 0 is 1. So I get a negative 1 on bottom. And finally, I get the answer of negative 6. Okay, now that was a problem we only could have done either graphically or using tables or using some sort of numerical method before. Okay, so it's opened up a new door for us here. How about this one? Well, I put in 1, I get 0. I take the natural log of 1, I get 0. And remember, why is natural log of 1 equal to 0? Because natural log has a base of e. It's asking us e to what power gives us 1. And of course, anything to the 0 power gives us 1. And that's why we get 0. So I can use L'Hopital's rule. So the limit, as x approaches 1, derivative of x minus 1 is 1. Derivative of natural log x is 1 over x. Okay, so now if I plug 1 in, 1 over 1, that is 1. Okay, so L'Hopital's rule, it's a pretty nifty little thing we can do here. Now, there's a bunch of examples here. I'll go through several of them, and we'll see how much time I have here, I suppose. Let me check out I'm going to make the bottom of my screen a little smaller if I can. Nope, I can't. I can't see how much time I have is my problem. I'm going to pause and come back. Okay, I moved it up a little bit. Now I can at least see how much time I have left. So I got about 7 minutes and 50-some seconds elapsed here. Okay, next one. Put 0 in for x. E to the 0 is 1. 1 minus 1 is 0. Put 0 in. Cosine of 0 is 1. 1 minus 1 is also 0. Okay, by the way, why is cosine of 0 1? Because 0 terminates on the positive x-axis where we cross the unit circle at 1, 0. Cosine is the x value. So cosine of 0 is 1. By the way, notice I'm doing this every time. You don't assume that you can use L'Hopital's rule. You have to verify it first. Even on the AP test, they'll give you a point for verifying that you get 0 over 0 and then going to this. Okay, so the derivative of e to the x minus 1 is e to the x. Derivative of cosine x is negative sine x. Well, I can see I'm no longer going to get 0 over 0. E to the 0 is 1. The sine of 0 is 0, however. Ugh. So I get 1 over 0. Now, what does that mean? Well, the numerator is approaching 1, a finite number, but the denominator is going to get smaller and smaller and smaller. It's going to approach 0. And what's important is to know that, think of what negative sine x looks like. Negative sine x kind of looks like this. It decreases through the origin rather than increasing, right? So it's approaching 0. From the left, it's approaching 0 from the positive side. And as we approach 0 from the right, we're approaching 0 from the negative side. Well, that's a problem. That means from the left of 0, I'm going to approach positive infinity. And as I approach 0 from the left, that is from the left, sorry. And then as I approach 0 from the right, I'm going to approach negative infinity. Well, if I'm approaching different things from two sides, we say this limit does not exist. Okay, so it still doesn't always work out great. We've got a form here where I don't know what 1 over 0 is, but I know 1 divided by something really tiny will be something really big. Okay, let's try the next one here. Okay, I put 0 in, 0 squared is 0. I put 0 in here, cosine of 0 is 1. 1 minus 0 is 1. So this answer is simply 0. I didn't need L'Hopital's rule. Okay, don't assume you'll always need it. Okay. Limit as x approaches 0, natural log of the natural log of x over natural log of x. Yeesh. So here we go. Put 0 in for x. Natural log of 0. Well, you can't even do the natural log of 0, right? So all you can do is approach 0. Okay. So this one's kind of a tricky one. In this case, the natural log graph looks like this. You notice I can't even approach 0 from both sides. I can only approach 0 from the right. If this had said 0 from the right, then you can see that it's going down to negative infinity. Okay, so as I put 0 in here, I get negative infinity. All right, so I'm taking the natural log of negative infinity. The only thing is I can't take the natural log of a negative. Okay, so here's a situation where you cannot even, you couldn't even do it if you're approaching 0 from both sides. This would not exist, basically, is what we're saying there. Okay, let's see, what else do I have here? The sine of x over the sine of x. Yuck, let's put 0 in there. Sine of 0 is 0, and then the sine of 0 again is 0. Sine of 0 is 0. Okay, so I can use it here. So limit as x approaches 0, sine of the sine of x. So that's going to need a chain rule, sine of junk. So the derivative of sine junk is cosine of junk times derivative of the junk, derivative of sine is cosine x. So it's going to be cosine of the sine of x times the cosine of x, all over the derivative of sine, which is cosine. So let's try that. Put 0 in for x. Sine of 0 is 0. Cosine of 0 is 1. Times cosine of 0 again is 1 over cosine of 0 again is 1. That one's equal to 1. So that one works out pretty nifty. Let's try the next one. Now in this one, you notice you have two fractions. So what might be helpful here is to first combine these two terms. So if you would have limit, and I haven't seen anything quite this difficult on an AP exam, but you could try to get a common denominator of x sine x would be your common denominator, and then rewrite each numerator. Okay, so this first fraction I had to multiply by sine x, so I got to do that on top. So I'll get, if I multiply that by sine x, I'll get sine x plus sine squared x minus sine x had to be multiplied, so minus x over x sine x. And by the way, if I would plug 0 in here, I would get 0. I would get 1 over 0 minus 1 over 0. I don't know what the heck that is. So that's why it's advantageous to try and get these together, see if L'Hopital's rule applies. So now, limit as x approaches 0. If I combine those numerators, I get sine x plus sine squared x minus x. Let's hope I can just get this in under the final bell here, over x sine x. So now we plug 0 in. I get 0 plus 0 minus 0 over 0 times 0. So it's definitely a 0 over 0. So now let's use L'Hopital's rule. So the limit as x approaches 0, the derivative of sine is cosine. Then I've got a chain rule. Junk squared would be 2 times junk to the first times derivative of sine is cosine minus the derivative of x is 1. All over on bottom I got a product rule. X cosine x plus 1 times sine of x. So I substitute in, I get 1 plus the sine of 0 is 0, so that's all 0, minus 1, so that's still 0. Here I get 0 times 1, which is 0, plus I got to do I get 0 over 0. I got to do the